called transistor biasing. So the basic function of the transistor, we know it is amplification. The process of raising the strength of the weak signal without any change in its general shape is referred to as faithful amplification. So generally amplifier is going to boost the weak signal, that is in terms of its voltage or current. So for faithful amplification, it is essential that the emitter base junction is forward biased. So generally if you take a BJT, we have emitter base and the collector, right? So the emitter base junction will be forward biased and the collector base junction will be reverse biased. So only in this mode it will behave as an amplifier. That is, we call this as the active region. We have studied the different regions of operation for BJT, right? So only in the active region it will work as an amplifier. So now when we are going to bias the transistor, we have to make sure that always the emitter base junction is forward biased, collector base is reverse biased, and there is a proper zero signal current, collector current. So it means zero signal means whenever we are not applying any input signal, that is any AC input signal, we are going to apply only DC input, that is VCC. VCC we call the DC power supply. We are going to get the collector current from the VCC. So when that collector current is called zero signal collector current, before applying any AC input, only through DC power supply, we are obtaining the collector current. That's called zero signal collector current. So the proper flow of zero signal collector current and the maintenance of proper collector emitter voltage during the passage of the signal is called transistor biasing. So we have to make sure that the transistor is working in the active region and there is proper DC collector current flowing from the supply. So all these are to be done. So how are we going to do this? Okay, we are going to make some arrangements in the circuit. Okay, so if the transistor is not biased, what will happen? So if the transistor is not biased properly, it will work inefficiently and produce distortion in the output signal. So we may not get the output signal properly, and we have to fix the operating point for the device. So that we call this as a Q point or the operating point. So once we fix the Q point, from there the AC signal will start amplifying. So that's why we need to bias the device. How it can be done? So how a transistor can be biased? A transistor is biased either with the help of a battery or associating a circuit with the transistor. So we need to apply some changes in the circuit. The latter method is more efficient and it's frequently used. The circuit used for transistor biasing is called a biasing circuit. So here we have different ways how to bias the transistor. We are going to have different methods of biasing, but now as of now we are going to study only one type of biasing. If you want, you can explore more. So I'm going to work only on voltage divider biasing, that we will be using it for the BJT amplifier design. Okay, so there are several methods. So here before that we will discuss about these concepts. What's called bias stability. So bias stability means we have, once you create the operating point, it has to be maintained stable. So that's called stabilization. So through proper biasing, a desired Q point or a quiescent operating point of the transistor amplifier in the active region, so or it's called the linear region of the characteristics, is obtained. So it is desired that once selected, the operating point should remain stable. So it should not get moved because of the ambient temperature changes or any other variations. The maintenance of the operating point stable, it's called as stabilization. The selection of a proper quiescent point generally depends on the following factors. First is the amplitude of the signal to be handled. So it depends on the signal input that we give, and also the load, that is whatever load we are going to connect. So based on these, the Q point will be dependent on these factors. The operating point of the transistor will shift mainly with changes in the temperature, since the transistor parameters, that is beta is the current gain. So for common emitter configuration, beta will be the current gain, and ICO will be the leakage current, collector leakage current, and the base emitter voltage. So these three parameters, they are functions of temperature. So once these changes, then it will change the operating point or the Q point. So we have to take care. So we have to choose a method where it is highly stable. The Q point, once it is fixed, it should be highly stable. So now what is called the DC operating point or the Q point, right? So here this is the VI characteristics that we have already studied for the common emitter amplifier. So can you recall common emitter amplifier? So this is the BJT common emitter amplifier, that is emitter terminal is grounded. This is the CE configuration. Emitter is grounded and input signal is given to the base. and output signal is taken at the collector, right? So this the way how we have connected the DC power supply, it's called as biasing now. And so based on the biasing, we are going to calculate the collector current and the collector to emitter voltage, that is IC and VC we will calculate. And we will fix these points, that is the maximum collector current and the maximum value of VCE. So these 2 points, once you connect, this is called as the DC load line. So this line is called the DC load line. So why it is called DC load line? Because we are not applying any AC input signal. Only with the DC power supply, we are calculating these 2 points, that is the collector current and the collector to emitter voltage. And the line that connects these 2 points is called the DC load line. And this is the Q point. Q point, here we have Q1, Q2 and Q3. Basically, we will fix only a single Q point, mostly in the middle of the active region. So these are the three operating regions, right? So the middle portion is called the active region, and the lower portion is the cutoff region, and this portion is the saturation region. So the operating point will be between the saturation and the cutoff point. That is, it will be exactly in the active region. For a transistor circuit to amplify, it must be properly biased with DC voltages. The DC operating point between the saturation and the cutoff is called the Q point. That is, we can choose anywhere between this cutoff and the saturation region, most probably in the middle of the active region. The goal is to set the Q point such that it does not go into saturation or cutoff when an AC signal is applied. So whenever after setting the Q point, you apply AC input signal, the signal level should not go to the saturation or the cutoff regions. Okay. So these are the requirements for biasing network. So we need to ensure proper zero signal collector current. That is, when you are giving VCC from the voltage source, we are going to get the collector current. You see here the collector current is flowing from here, right? So this is the DC current without applying any input signal. And you can see from the supply that is given to the base current is flowing to the base. So all these are the DC currents, the base and the collector currents. So we need to ensure proper zero signal current, collector current, and ensuring VCE, the collector to emitter voltage, not falling below 0.5 volts for germanium transistor and 1 volt for silicon. So all these are some of the basic requirements, and we need to ensure that it is highly stable. Once the operating point is fixed, it should be stable. Okay. So we define one more parameter, which is called the stability factor. So this stability factor will be the ratio of change in the collector current to the change in the collector to that is ICO, reverse saturation current. This is called the stability factor. So it depends on the collector current and ICO. Whenever there is a change in the collector current, this stability factor will change. Okay. So this is just a definition of the stability factor, how we are maintaining thermal stability of the operating point. Okay. So let us go to the biasing. That is what we call as potential divider or voltage divider biasing. So these are the different methods for biasing the transistor. First method is called fixed bias, and fixed bias with emitter resistor, collector to base bias, and then the potential divider bias. So now we will study only about this method, last method, which is called potential divider or voltage divider or self bias. So we call it in different names. Okay. Can you draw this circuit for voltage divider bias? Please draw this. Okay. So now we have the common emitter configuration here. So this is the base and the emitter, and the emitter terminal is grounded, and this is the collector terminal, and we have the collector resistance RC, and this RE is the emitter resistance, and R1 and R2 are the resistance which is for the biasing. Okay. And so from VCC, this is the power supply. So this IC is the collector current that is flowing. So this is called the zero signal collector current. So zero signal means without applying any AC signal. This is, we are obtaining this collector current from the directly from the supply. VCC is producing this IC collector current, the DC current. Now, and this is the base current entering the base, and this sum of this IC and IB will be equal to the emitter current, right? And this is the base emitter voltage. And now we are calculating what will be the equivalent voltage, that is VT at this junction, that is the base. So why do we calculate this is, so now we are going to take this loop, and we are going to calculate VT. So by calculating this, we are basically calculating the base current. So through the base current, we are going to calculate the collector current once knowing the current gain. So basically, through this biasing method, we are going to calculate the 2 points, 2 operating points, that is the collector current and the collector to emitter voltage, that is IC and VCE. So we are going to draw the DC load line connecting IC and VCE. So for this, we need to calculate IC and VCE. What is the maximum value of IC and VCE? Now, through this biasing method, we are going to calculate IC and VCE. So now, this is one of the simple circuit used to establish a stable operating point in the self-biasing configuration. So this method is highly stable. For a transistor to remain in the active region, the base emitter junction has to be forward biased. And this is R1 and R2 for the resistance. These are used for the biasing. And now this equivalent circuit is the Thevenin equivalent. So Thevenin equivalent means, have you studied anything about Thevenin's and Norton's theorem? Anytime have you studied? Okay, so now we are going to convert this R1 and R2 into equivalent resistance, Thevenin equivalent resistance, and we are going to find what will be the equivalent voltage here. That VT is called the Thevenin voltage, the equivalent voltage. So now we are just going to that is change this circuit, something like this to this. Okay, and you can see here R1 and R2 are in parallel connection, and VCC is the voltage that is applied across this R1 and R2. Okay, and now we are going to calculate the voltage drop across this resistor R2, or the equivalent voltage, the Thevenin voltage across this R2. So we can calculate this voltage VT as this applied voltage, total voltage VCC, into this parallel resistance R2 divided by sum of the resistance R1 and R2. That will give the Thevenin voltage VT. So always we have to calculate like this. This Thevenin voltage is calculated as the applied voltage into the parallel resistance, where we are calculating the voltage drop that across that resistance R2 divided by sum of the resistances R1 and R2, the parallel resistances. So accordingly we calculate VT, right? And here we are, and again, so now you have calculated and we have converted into this like a loop, and this R1 and R2 will be equivalent to one equivalent resistance, that is the base resistance, or we can even call this as a Thevenin equivalent resistance. So this base resistance can be written as the parallel combination of R1 and R2. So this will be R1 R2 by R1 plus R2. This circuit is transformed like this. Okay, you please draw the circuit, the Thevenin equivalent circuit, after we transform. Or you please refer it later. Okay, well, let us see the equations. Now, once you transform this circuit into this, the Thevenin voltage is the parallel resistance R2 into the applied voltage divided by sum of the two resistances. And the base resistance or the Thevenin equivalent resistance will be the parallel combination of R1 R2, which is R1 R2 by R1 plus R2. So please take this equation.
Yes, ma'am.
Okay. Now, so we are going to take this loop, that is we are going to apply KVL to this base loop. Okay, applying the loop equation to the base circuit, we are going to write this VT equal to IB into RB, that is this current into this resistance, plus the base emitter voltage of the junction, base emitter voltage VBE, plus we can write IE into RE, or this emitter current we can write it as sum of the base current plus the collector current, that is plus IB plus IC into RE, right? So we are going to write this KVL equation in this loop. Okay, based on using this equation, we can find the value of base current. Through the base current, we will find the collector current. Okay, using this equation. And now we are going to apply the KVL at the collector side, that is collector circuit. Here we can write this VCC, this the supply voltage will be equal to the drop across this portion, that is the collector resistance, and the drop across this collector to emitter, that is VCE, we can mention as VCE, and the drop across this emitter resistance. We can write this total supply will be equal to the voltage drop across this collector resistance and the collector to emitter terminals and the emitter resistor. So we can write the equation VCC equal to IC into RC plus VCE plus IE into RE. So through that equation, we can bring VCE on one side because we want to calculate VCE in order to calculate the that is fix the operating point, the DC load line. So we are rewriting the equation in terms of VCE. It is equal to the total supply VCC minus the voltage drop across the collector resistance and the emitter resistance.